Hi, welcome to Numerical Integration. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. Chapter 4, Integration, comes to us from Larson's 11th edition calculus text. This is for calculus, obviously. Section 4.6, Numerical Integration. So sometimes there are integrands that we just can't handle. And this will be no matter how high up you go in your calculus adventures or in your math pursuits. And we need ways to estimate our areas. And the trapezoidal rule is one of those ways. Let f be continuous on the closed interval from a to b. The trapezoidal rule for approximating the antiderivative from a to b of f of x dx is given by the approximation is b minus a, the length of the interval, divided by 2n, multiplied by f of x0 plus 2 times f of x1 plus 2 times f of x2, and so on. And I once again forgot to close that parenthesis. Moreover, as n approaches infinity, the right-hand side approaches the definite integral. The most important part, I would say, is how do we find these values? What are the x sub i's? If I have any interval cut from a to b, maybe n equals 4, and I have 4 intervals. Well, here I'll have x0. This will be x1, x2, x3, and finally x4. So my endpoints of the subintervals based on my n, the number of intervals we're creating for our a to b, they're going to give you the endpoints. That's an x2, the 2 didn't show up. That's a b, which is also x sub 4 in our sum. Notice that the endpoints we do not multiply by 2, but the rest of them we do. And that 2 is handled as kind of a canceling out because of that. The endpoints double, and then everything else doubles on itself. Here we go. We're going to use the trapezoidal rule to approximate the integral from 0 to pi of sine of x dx using both n equals 4 and n equals 8. And we're going to compare that to the actual value because the integral from 0 to pi of sine of x dx is something that we can do. So we can find this actual value. Here we go. When n equals 4, delta x is pi over 4, right? So going from 0 to pi, and I want to cut it into 4 pieces, so each piece will have a length of pi over 4. Therefore, the integral from 0 to pi of sine of x dx will be pi minus 0, which is pi, over 2 times n, 4 times 2 is 8, times sine of 0 plus 2 times the sine of pi over 4 plus 2 times the sine of pi, 2 pi over 4, right, the second subinterval, but we'll simplify that to pi over 2, plus 2 times the sine of 3 pi over 4, plus 1 times the sine of 4 pi over 4, which we just call the sine of pi. So my interval from 0 to pi is cut into 4 pieces. Those 4 pieces are marked by 0, pi over 4, pi over 2, 3 pi over 4, and pi. Those are the x sub I values from the rule. Evaluating the sine of 0 and the sine of pi, I get zeros. The sine of pi over 4 and the sine of 3 pi over 4 are each square root of 2 over 2, but the 2 coefficients cancel out our denominators. The sine of pi over 2 is 1, 1 times 2 is 2, and pi over 8 multiplied by this sum will give us an estimate of 1.896. So it seems as though the area under the curve of the sine of x from 0 to pi is approximately 1.896. But what if we're using an n value of 8? Well, cutting the interval from 0 to pi into 8 pieces, each will have a length of pi over 8. So we'll have b minus a is pi over 2 times n, 2 times 8 is 16. Sine of 0 plus 2 times the sine of pi over 8 plus 2 times the sine of pi over 4, and so on, all the way up to 2 times the sine of 7 pi over 8 plus the sine of pi. Again, the sine of pi and the sine of 0 are both 0. The sine of pi over 4 and the sine of 3 pi over 4 are both square root of 2 over 2. They both have a coefficient of 2, so those cancel out. So they're each square root of 2, and I'll have 2 of them to make 2 square root of 2. The sine of pi over 2, which is 4 pi over 8, is 1. 1 times 2 is 2. And then I'll have the sine of pi over 8, which I don't know the value of, but I know it's the same as the sine of 7 pi over 8. So I can rewrite that as 4 sine of pi over 8. And here I have the 2 times the sine of 3 pi over 8. And on the other side, I have the sine of 2 times the sine of 5 pi over 8. The sine of 3 pi over 8 and the sine of 5 pi over 8 are the same value, so we'll just call them 4 using a representative, a sine of 3 pi over 8. I can enter this in my calculator to get 1.974. Do I have to find these values? No. I can enter this in my calculator using parentheses for the argument of the sine just from this step. I can enter them here. And my approximation is 1.974. Notice that is closer to 2 than our previous estimation. But what's the actual value? We know the antiderivative of sine of x dx is a minus cosine of x. And we know that when we have a definite integral, we need to evaluate, which is what this line means. We're going to evaluate minus cosine of x from 0 to pi. So that's a negative cosine of pi minus a negative cosine of 0. 1 plus 1, which is 2. When n equals 4, we got a decent approximation. But when n was 8, we got even closer. Think what we could do if n equals 10 or 12 or double it. N equals 16, we'll probably be right at 2. So these approximations get us very, very close for the more subintervals that we have as n gets larger. We also have Simpson's rule. Let f be continuous on the interval from a to b, and let n be an even integer. So this only works if you're dividing your interval from a to b into an even number of subintervals. Simpson's rule is then the approximation for the integral from a to b of f of x dx is b minus a over 3n multiplied by f of x0 plus 4 f of x1 plus 2 times f of x2 plus 4 times f of x3. So we alternate. The endpoints are not multiplied by anything, but then we multiply by with coefficients of 4, 2, 4, 2, 4, and so on. And that's why our n value has to be in even integers, so our pattern works out. As n gets larger, the more subintervals we have, the right-hand side approaches the value of the definite integral. So if you want a better approximation, use more subintervals. So we're going to use Simpson's rule and the trapezoidal rule to estimate a derivative and then compare it to its actual value. The integral from 2 to 3 of 2 over x squared dx when n equals 4. First, we're going to partition the interval from 2 to 3 into 4 intervals. So I'll have subintervals ending at 2.25, 2.5, and 2.75. My trapezoidal rule says b minus a over 2 times n, f of 2 times 2 times f of 2.5 plus 2 times f of 2.25, 2 times f of 2.5 and 2 times f of 2.75 plus f of 3. The endpoints never multiplied by any values in these estimates, and that's because together they make up a, quote, 2. 3 minus 2 is 1. 2 times 4 is 8, so I'll have 1/8. And I could evaluate this function, right? My function is 2 over x squared. Or I could just type in exactly what it is. Don't forget our coefficients of 2 here, making our numerators 4. And my estimate is 0.3352. Cool, it's pretty close to a third. Let's see how it goes. Using Simpson's rule, same partition. 3 minus 2 over 3 times n. Same values, only now my coefficients are 4, 2, and then 4. Endpoints never multiplied. Simplifying, using a calculator, I get 0.3334. That's a lot closer to a third than the previous one was, but it's still pretty close to just a third. So what's the actual value? Well, we know that the actual value of the integral from 2 to 3 of 2 over x squared dx, the 2 comes out in front. The antiderivative of x squared is the antiderivative of x to the negative 2. And the antiderivative of x to the negative 2 is x to the negative 1 over negative 1. And we can simplify with that 2 coefficient that came from our numerator. That's a 3. Boy, that's an ugly looking 3, isn't it? put in a 2, which looks like a z, and a 3. I don't even know what that looks like. When I evaluate negative 2 over x from 2 to 3, I get negative 2/3 minus negative 2/2. Subtracting a negative, that's negative 2/3 plus a whole, which is a positive 1/3. 0.3333. Look how close Simpson's estimate is. It's an even better estimate than the trapezoidal estimate, but you have to have an even number of subintervals. The trapezoidal will work with n equals 7, n equals 13. Any of your favorite unlucky numbers will work just fine. So, what about a function that we can't compare? The integral from pi over 2 to pi of the square root of x sine of x dx when n equals 4. Trapezoidal rule to approximate this. We'll have b minus a, so pi minus pi over 2 times n. N is given to us as 4. F of pi over 2 plus 2 times f of pi, 5 pi over 8, and so on, right? So I'm dividing it by 4. I'm going to increase by 8ths each time because this distance. And when I'm evaluating f of pi over 2, just so we can see exactly what this is, f of pi over 2 is the square root of pi over 2 times the sine of pi over 2. And it'll be the same for all of them. F of 5 pi over 8 will be square root of 5 pi over 8 times the sine of 5 pi over 8, and so on. And you can see where absolutely we're going to use a calculator to evaluate these, and I get the approximation of 1.4299. Using Simpson's rule, b minus a over 3 times n. The only change is my coefficients of 4, 2, 4. Right? The endpoints never multiplied. Again, f of pi over 2, I'm going to evaluate my integrand at pi over 2, 5 pi over 8, 3 pi over 4, and so on. And when I enter this in my calculator, I get an approximation of 1.4583. The actual value is one that we can't actually find the antiderivative of with our current skills, but with a computer algebra system or a graphing calculator that can do integrals, and actually any of the graphing calculators can do definite integrals, we find that the antiderivative, the integral from pi over 2 to pi, the square root of x sine of x dx, is approximately 1.4579. Again, the trapezoidal estimate, 1.4299. The Simpson's estimate, 1.4583, 1.4579. Simpson's is a great estimate. It's always a little bit closer than the trapezoidal, but, you know, trapezoidals are close enough, good enough, it gives you an idea. That is it for numerical integration. Thanks for listening.